Okay, here's a video on equations of planes. Okay, so when we're talking planes, we're talking this thing here. So we're going to talk about planes in 3 space. So we've got an X, Y, and a Z axis. And this is kind of how we draw a plane. It's kind of hard to draw one because they actually do go out in all directions forever and ever. But we kind of just draw it as like a rectangle or a parallelogram or something like that shape. But it does keep going in all directions. That's what it looks like. Okay, now what does the equation of a plane look like? So there's multiple forms of an equation, but let's start with a scalar form. Okay, so when we're working in 2 space, we know that this x plus 2y minus 8 equals 0 defines a line. And I graphed it for you. So this is what a line looks like, and this is the scalar equation of a line. Now remember we said we can't make a scalar equation of a line in 3 space? We can't. And the reason is because of this plane thing that we're gonna do. So it turns out once you add a z component here, so once you make it, instead of just like ax plus by plus c equals 0, once you stick in an ax plus by plus cz plus d equals 0, you're actually creating the equation of a plane now. And why is that? It's because, check out this line. Like if I were to graph this line in 3 space, like just rough sketch, so I got like, I don't know, something like this. That's my line. As soon as I start adding different z points, so like for example, this point right here is the point 0, 4. If I added a z component to it, like let's say it was 0, 4. Look, let's say this this equation, let's say I add like 0z minus 8. Like I could literally put in anything for z to make this equation true. So if I put like a 0 in there, and then I graphed that, and then next time I put 0, 4, 2, and then I graphed that. So now I'd be graphing it like up here. And let's say I did that with all the points. So I'd be graphing like all these points. They'd just be going up the z-axis, right? But you'd be staying on that same plane, I guess. So you'd be graphing all these same points, but in different locations. Essentially, you're creating, I'll just use my highlighter, you're creating the equation of a plane when you add this extra term for z. So there's no scalar equation of a line in 3 space because it becomes your scalar equation of a plane in 3 space. Okay, so that brings us to this. The scalar equation of a plane in 3 space is ax plus by plus cz plus d equals 0. So that's how we write the scalar equation of a plane. Okay, so let's look at it more closely. Okay, so let me give you an equation. X plus 2y minus z minus 8 equals 0. There is the scalar equation of a plane. So this describes a plane in 3 space. So I can ask you questions like, is this point on the plane? So I want to know if this point is on the plane. So I've got some kind of plane. Is that point on it or is it somewhere else? Okay, so we can just sub it in and see if the left side equals the right side. So let's try it. So the left side of the equation would be, after I sub it in, 1 plus 2 times 3 minus negative 1 minus 8. So let's check. 6, 7, 8 minus 8, 0. And the right side is equal to 0. So the point is on the plane. So we can test if points are on planes. What else can we do with planes? We could also find x and y-intercepts of planes. So we can find out where's the plane cross the x, y, and z axis. So let me just show you that. I'll just switch colors. Okay, so if you wanted to find the intercepts, let's say you wanted to find the x-intercept. Then you would just sub in 0 for y and z. So x plus 2 times 0 minus 0 minus 8 equals 0. So all that 0 stuff is gone, so x equals 8. So I found my x-intercept. And I could do the same thing for y and z. So to find the y-intercept, I could sub in 0 for x and z. And to find the z-intercept, I can sub in 0 for x and y. So I'm able to check if points are on planes. I'm able to find intercepts. And I can even find vectors that are parallel to my plane. So I've got this plane, and I want to find a vector that's actually parallel to my plane. And I can do that using points on the plane. So let's say I wanted to find a vector that's parallel to my plane. Okay, so I know, what do I know? I've got this point on my plane, 1, 3, negative 1. Okay, so I've got the point 1, 3, negative 1 on my plane. What if I wanted to find another point on my plane? You know what? You can find as many points on a plane as you want to by just satisfying this equation. So let's try to do that because I need another point. Just gonna move that over. Okay, I'm gonna add it to here. Okay, so I need to find another point on my plane. So x plus 2y minus z minus 8 equals 0. I'm just looking to find a point. So you know what? You can just make stuff up for x, y, and solve for z if you want, or make something up for 2 of them and solve for the third. Okay, so I'm gonna make y, I don't know, 0. I'll make z 3, just randomly. And then I'll solve for x. So x would equal, so 2 times 0 is 0, negative 3 minus 8 is negative 11, so positive 11. So now I just created the point 11, 0. Oh, I guess that would be positive 3, right? Because that, okay. So I found the point 11, 0, 3 is on my plane. It's like an odd point, but yeah, just randomly picked it. So I'll call that point B. You can find tons of points on your plane by just making up x and y or x and z, or just pick 2 variables and make something up for them and solve for the third. So if I wanted to find a vector that's parallel to my plane, I can use 2 points on my plane, because just picture this. So let's say I have point A and point B. To find a vector that's parallel, I can find the vector AB or BA. So if I find vector AB, that would be 11 minus 1, so 10, 0 minus 3, negative 3, and 3 minus negative 1, so 4. So I just found a vector that's parallel to my plane. And I could find tons of them. Okay, we also are able to make vector equations of planes. So I'll just show that. So we can actually create vector equations of planes. Vector equations of planes. And vector equations of planes look like this. R equals R naught plus a parameter t. And then I'll say vector A plus a parameter s multiplied by vector b. So basically, a vector equation of a plane is different than the vector equation of a line because we added an extra direction vector. So in order to describe a plane, we need to know 2 direction vectors. We need to know 2 direction vectors that aren't parallel. And we need a position vector, or just a point on our plane, because that will be our position vector. So basically a point on the plane and 2 direction vectors. Or if we don't have all that information, we could get by with just knowing 3 points on the plane. Because 1 point could be used for our position vector, and then we could get 2 direction vectors using those 2 points. Oh, and you know what? While we're at it, from the vector equations, we can also get parametric equations of planes. So we can still split up our vector equation into the x, y, and z component.